Every winter, China spends more than $500 million to build a massive city that exists for exactly 30 days. To make it happen, more than 10,000 workers cut through frozen rivers before transporting millions of ice blocks to construct the largest illuminated ice wonder on Earth. This is not only an engineering battle against the limits of nature, but also an ambitious effort to transform the harsh winter into a new engine of economic growth for northeastern China. So how do Chinese engineers build an entire giant ice city in just a few weeks? Join Agriculture Insight as we uncover the story behind this extraordinary achievement. China did not build this $500 million wonder to last forever. It was built to disappear completely. Every winter, an entire giant ice city rises, only to melt away when spring arrives. Deep in northeastern China, where the temperature difference between summer and winter can reach nearly 80 degrees Celsius, Harbin possesses one of the rarest natural environments in the world. Every year, the Songhua River, stretching nearly 2,000 kilometers, freezes solid, creating an enormous supply of building material that nature produces for free. Yet having an abundant source of ice is only the beginning, because the greatest challenge lies in the very nature of the material itself. Unlike concrete or steel, ice constantly cracks under vibration, deforms as temperatures change, and begins melting the moment it is removed from the frozen river. That turns the entire project into a race against both time and climate, pushing against almost every principle of modern construction. But if those limits can be overcome, Harbin will not only create the largest illuminated ice wonder on Earth, it will also become a symbol of the more than $140 billion ice and snow economy. Far beyond an ice festival, it is part of a broader strategy to transform the region's harsh winter into a new engine of economic growth for northeastern China. In other words, it is proof of how this nation transforms a land of extreme climate into almost limitless potential. That is why, every year, the country launches what seems like an almost impossible mission, cutting through the frozen Songhua River and constructing an entire glowing mega city in just 30 days before spring arrives to destroy it all. And to understand how Chinese engineers make this possible, we have to begin with the very first step: harvesting enormous blocks of ice from the frozen Songhua River. Around the beginning of December each year, when a layer of ice nearly 1 meter thick covers the Songhua River, more than 10,000 workers transform the entire river into a massive construction site. But before the first saw touches the ice, engineering teams continuously survey the thickness of the frozen surface to identify areas strong enough to support heavy machinery weighing tens of tons. The entire river surface is then marked with standardized cutting lines, dividing it into tens of thousands of uniform ice blocks. Unlike ordinary artificial ice, the natural ice from the Songhua River has a higher density, contains fewer air bubbles, and reaches a purity of up to 99%. These unique properties allow LED light to penetrate deep inside each block, creating the crystal-clear glowing effect that has become the signature of Harbin Ice and Snow World. At this stage, high-powered industrial saws cut long grooves through the ice layer, which is nearly 1 meter thick. Once the main industrial cuts are complete, workers use long steel chisels to break the remaining ice connections underneath and control the separation of each individual block. The entire process must be completed as quickly as possible before cracks begin spreading through the ice structure. After each block is separated from the ice below, it is attached to a mechanized rail pulling system that slides it directly from the water onto the frozen river surface, This method reduces vibration and distributes force more evenly than lifting the blocks straight up with cranes, minimizing the risk of cracking large ice blocks. The scale of this operation is almost unmatched in the field of ice construction. Every year, Harbin Ice and Snow World requires more than 400,000 cubic meters of ice and snow to build structures covering approximately 1.2 million square meters. But harvesting the ice is only the beginning. The real challenge is how to transport and store tens of thousands of these massive ice blocks for months before they begin to melt. After sorting is complete, thousands of ice blocks weighing hundreds of kilograms each are continuously transported by forklifts and heavy-duty trucks from the Salnois River to the main construction site. At the site, the ice blocks are not used for construction immediately. Instead, they are stockpiled in enormous outdoor storage yards, stacked in large layers resembling industrial shipping containers. But the moment they leave the frozen river, the countdown begins. To extend their usable lifespan, the ice blocks are covered with multiple layers of insulating materials, including straw, fiber mats, and specialized industrial insulation blankets, all designed to slow the absorption of heat from the surrounding environment. Thanks to this preservation system, the temperature inside the core of each ice block can be maintained at approximately -15 degrees Celsius for an extended period, allowing the blocks to retain their crystal clear appearance while preserving their structural integrity. What makes this even more remarkable is that this entire logistics system, including thousands of vehicles, vast storage yards, and specialized insulation materials, exists for a single purpose: extending the lifespan of a material that is melting away minute by minute under the relentless passage of time. The most common misconception among visitors is that every structure in Harbin is built entirely from solid blocks of ice. In reality, behind those crystal-clear towers stands a massive steel framework that serves as the invisible skeleton of the entire city. The reason is simple. Ice performs well under compression, but it is far weaker under tension and bending. For that reason, construction crews begin by building temporary foundations and anchoring steel columns directly into the frozen river surface and the frozen ground beneath it. Thousands of steel modules are then assembled to form a structural framework capable of resisting twisting, vibration, and the powerful winter winds blowing from Siberia. But the taller the structures become, the greater the challenge. Each ice block, weighing hundreds of kilograms, continuously increases the load on the entire framework, while the temperature difference between day and night causes the ice to expand and contract without stopping. That forces engineers to calculate every connection point with precision, ensuring that each structure remains stable throughout its entire operating period. Despite covering an area of nearly 1.2 million square meters, the entire steel framework must be completed in just 15 days to keep the construction schedule on track. After nearly 10 months in storage, the ice blocks harvested during the previous winter finally begin leaving the preservation yards to enter the most critical stage of the entire logistics system: transportation to the Harbin Ice and Snow World construction site. At the outdoor storage yards, workers first remove the natural insulating layers that have been used to slow the melting process for weeks. They carefully strip away every layer of straw, fiber mats, and insulating materials that has protected the ice throughout the past several months. Industrial forklifts then separate each individual block from the massive ice stacks before loading them onto heavy-duty trucks. But unlike concrete or steel, the countdown for every ice block begins the moment it leaves the storage yard. Each block continuously absorbs heat from its surroundings, while every impact and vibration during transportation can create cracks that reduce the quality of the material. That is why the entire transportation system must operate almost without interruption. And as the final truckloads arrive at the construction site, the most complex phase of the entire project truly begins, transforming hundreds of thousands of crystal-clear ice blocks into giant illuminated towers that shine throughout the winter. This is no longer ordinary ice sculpting. It is a mega engineering project where the limits of materials, climate, and time are all pushed to the extreme. Once the steel framework is complete, industrial cranes begin lifting ice blocks weighing hundreds of kilograms to heights of tens of meters. At that point, workers must trim and align each block directly on the structure so that every joint fits together with almost perfect precision. What makes the process remarkable is that Harbin uses almost no cement or chemical adhesives. Instead, water is poured into the joints between the ice blocks. At temperatures of around -30 degrees Celsius, the water freezes almost instantly, creating a natural weld that bonds the blocks into a single unified structure. At the same time, freezing winds from Siberia sweep continuously across the construction site, where temperatures remain below -30 degrees Celsius. Metal surfaces freeze rapidly, while the human body loses heat so quickly that even the simplest tasks become increasingly difficult after hours of continuous work. In approximately 15 days, more than 150,000 ice blocks come together to form towers rising tens of meters into the air, creating the largest architectural structures of Harbin ice and snow world. After the central ice towers are completed, Harbin continues by constructing one of the festival's most popular attractions, one of the longest ice slides in the world. Measuring 521 meters in length, featuring 24 sliding lanes, and built with approximately 15,000 cubic meters of ice, it is no longer just a winter attraction, but an engineering challenge centered on the physics of motion. If the slope is too steep, riders can reach dangerous speeds within just a few seconds. But if the surface generates too much friction, or if the transition sections are not engineered with precision, the entire system can become unstable and significantly increase the risk of collisions. That is why, before the final layer of ice is applied, workers build a foundation of multiple compacted snow layers to ensure the stability of the entire slide. The ice surface is then applied and continuously polished to create a finish that is hard enough, smooth enough, and has the proper coefficient of friction, allowing riders to reach high speeds while remaining safe. Every day, the sliding surface must be continuously inspected, re-leveled, and adjusted to ensure that thousands of visitors can use it safely despite constantly changing temperatures. If ice is used for structure and illumination, then snow is what defines the entire visual language of Harbin. It is the material used to create giant castles, towering sculptures rising tens of meters high, and fantasy-inspired structures stretching throughout the park. But unlike what many people imagine, these creations are not built by manually adding one small layer after another. Instead, the snow is first compressed under high pressure into high-density blocks that are stable enough for large-scale construction. Artists and workers then use saws, shovels, and specialized cutting tools to continuously remove excess material until the final form gradually emerges. In essence, snow sculpting is not the process of adding material. It is the process of removing material to reveal the structure hidden within the massive block of snow. Using approximately 150,000 cubic meters of snow, Harbin creates more than 260 monumental structures and sculptures, completing an ice and snow world that spans millions of square meters in the heart of northeastern China's winter. Once every ice structure is complete, Harbin enters the final stage, transforming the entire city into a giant wonder of light. Tens of thousands of multicolored LED lighting units are installed inside the ice blocks, creating a brilliant glowing effect as the light passes through the crystal-clear ice. In just 30 days, more than 400,000 cubic meters of ice and snow are transformed into one of the largest temporary ice cities in the world. As night falls, the entire wonder becomes a vast network of illuminated architecture spanning more than 1 million square meters, creating the most iconic symbol of Harbin ice and snow world. Unfortunately, only a few weeks after reaching its most spectacular moment, rising temperatures cause this glowing city in the Siberian winter to gradually disappear. Yet despite existing for only a short time, Harbin Ice and Snow World has become one of the defining symbols of the winter economy. During the 2024 to 2025 winter season alone, Harbin welcomed more than 90 million visitors and generated more than 137 billion renminbi in tourism revenue, equivalent to nearly $19 billion. And perhaps the most extraordinary achievement is not that Harbin can exist amid ice and snow, but that people have learned how to transform winter itself into an industry. So what do you think? Is building an entire $500 million city only to watch it melt away the greatest waste in history, or the ultimate demonstration of modern engineering? Every spring, this city disappears, and every winter, the battle against ice begins all over again. The paradox of Japan is that the very advantages that created its prosperity have also become its greatest vulnerability. Surrounded by the ocean and blessed with more than 35,000 kilometers of coastline, Japan has been forced to concentrate most of its population, major cities, seaports, industrial zones, and its most fertile plains along the Pacific coast. Yet this same coastline sits at the convergence of 4 major tectonic plates, making it one of the most seismically active regions on Earth. Whenever the seafloor is displaced by a powerful earthquake, the entire column of water above it is pushed upward, generating tsunami waves capable of traveling at speeds of nearly 800 kilometers per hour. As they move into shallow coastal waters, the waves rapidly increase in height, transforming into enormous walls of water that surge directly onto the land. That is why Japan has repeatedly suffered some of the most devastating tsunamis in the world. The disaster in 2011 alone claimed the lives of more than 18,000 people, destroyed more than 123,000 buildings, and triggered the most severe nuclear crisis since Chernobyl. Total economic losses exceeded $220 billion, making it the costliest natural disaster in modern history. But that was not the only price Japan had to pay. With only about 12% of its land suitable for cultivation, every major tsunami devastates precious coastal plains while threatening the limited farmland that feeds the entire nation. Instead of simply responding after disasters, the Japanese turned adversity into a catalyst for innovation, building one of the most advanced disaster defense systems in the world. So how can this Great Wall, stretching nearly 400 kilometers, protect millions of people, safeguard agricultural regions that produce millions of tons of crops every year, and defend the world's 4th largest economy? To understand this extraordinary achievement, we must first go back to the moment when Japan decided to do what many believed was impossible. The first step was to create the most detailed tsunami risk map ever developed. Engineers gathered dozens of layers of data, including records of earthquakes and tsunamis spanning centuries, seafloor topography, ocean depth, the shape of coastal bays, shoreline gradients, and the locations of cities, seaports, industrial zones, and critical agricultural plains. This information was then fed into hydrodynamic models running on supercomputers. Instead of simulating a single scenario, the system calculated thousands of different possibilities. Based on these simulations, engineers determined the height, length, location, structural design, and level of reinforcement required for each section of the wall, ensuring it is tailored to the terrain and tsunami risk of every coastal area. In other words, Japan's Great Wall was not built to follow the coastline. It was built to follow the path of risk. For Japanese engineers, the first enemy was not the tsunami, but the unstable coastal ground itself. After thousands of years of sediment deposition, many coastal areas were formed from sand, mud, and soft sediments that could not support the enormous weight of massive concrete seawalls. In areas with weak ground conditions, reinforced concrete piles or steel piles measuring between 20 and 40 meters in length were driven or drilled into stable soil layers, transferring the entire load of the wall to the foundation below. In many locations, the ground was further reinforced with crushed stone, geotechnical materials, or advanced soil improvement technologies to reduce settlement and prevent soil liquefaction during earthquakes. Only after the foundation was strong enough could construction of the tsunami seawall truly begin. Instead of pouring concrete continuously along the entire length of nearly 400 kilometers, engineers divided the project into thousands of independent sections. This allowed construction to proceed simultaneously at multiple locations while limiting the impact if any section were damaged in the future. First, reinforced steel cages were assembled directly at the construction site and positioned on the completed foundation system. Next, high-strength concrete was continuously pumped into the formwork using specialized concrete pump trucks. Every layer of concrete was mechanically vibrated to remove air pockets, increase density, and minimize cracking after curing. Once the concrete reached its designed strength, the individual sections were connected to form a continuous defensive barrier. Depending on the terrain and the level of tsunami risk, the wall ranges from 5 to 15 meters in height, while its foundation is anchored as deep as 25 meters below the surface. The base of the wall is also significantly widened to distribute structural loads, resist overturning and sliding, and reduce erosion under the immense force of tsunami waves. However, the purpose of the wall is not to defeat the ocean. In many locations, additional layers of large armor rocks, wave-dissipating concrete blocks, and reinforced sloped embankments are installed in front of the wall. These structures absorb part of the wave's energy before it reaches the seawall itself, while also reducing foundation erosion and extending the lifespan of the entire defense system. Interestingly, the Japanese have never considered the Great Wall to be their only line of defense. If a tsunami powerful enough were to strike, no wall could guarantee stopping millions of tons of water rushing toward the land. Instead of trying to conquer nature, the Great Wall is designed to slow it down. By reducing the height of the waves, absorbing part of their energy, and delaying their arrival by just a few minutes, the early warning system gains enough time to issue alerts, evacuation routes can be activated, and millions of people have a chance to escape the danger. That is why, behind the wall, an entire network of seismic sensors, wave monitoring buoys, warning sirens, and evacuation routes operates as one unified system. But the greatest value of this defensive barrier is not the wall itself. It is what the wall protects behind it. It protects Japan's limited coastal plains, which produce millions of tons of agricultural products every year and help sustain one of the most productive agricultural systems in the world. With about 80% of its territory covered by mountains, Japan has only about 12% of its land suitable for cultivation. Most of this limited farmland is concentrated on fertile coastal plains, the very areas that face the constant threat of earthquakes and tsunamis. That is why every square meter of land behind the Great Wall carries extraordinary importance for the nation's food security. Among these precious resources, rice has always been regarded as Japan's second line of defense. During harvest season, GPS-guided combine harvesters automatically move through the rice fields with an accuracy of just a few centimeters, cutting, threshing, and cleaning the grain in a single operation. This highly mechanized process speeds up harvesting, reduces crop losses, and preserves grain quality before the rice is dried, milled, and sorted. Every year, more than 1.4 million hectares of rice paddies produce approximately 7 to 8 million tons of rice, supplying the primary food source for more than 120 million people across Japan. Unlike many countries that can expand their agricultural land, Japan has virtually no additional farmland to replace its coastal plains if they are devastated by tsunamis or contaminated by saltwater. In a country where expanding farmland is almost impossible, the value generated from every square meter matters more than total production. And Wagyu is perhaps the clearest example of that philosophy. With limited land available for livestock farming, Japan does not compete by raising larger cattle herds like the United States or Brazil. Instead, the country focuses on genetic selection, herd management, and quality optimization to produce one of the world's most valuable types of beef. For approximately 28 to 36 months, the cattle are fed carefully formulated rations consisting of hay, rice straw, corn, barley, and various energy-rich grains. This controlled feeding program regulates growth while encouraging the formation of the fine marbling that develops throughout the muscle. The extended feeding period creates Wagyu's signature tenderness, rich flavor, and its world-famous melt-in-your-mouth texture. For Japan, Wagyu is far more than just beef. It is a multi-billion-dollar industry with a domestic market worth nearly $11 billion and annual exports exceeding $400 million, making Japan the global leader in the premium beef segment. Even after protecting its land from tsunamis, Japan still faced another major challenge: too little farmland and an increasingly aging agricultural workforce. Instead of expanding agricultural land, the country chose to increase productivity on every square meter through high-tech greenhouses. Today, Japan operates approximately 43,200 hectares of greenhouses, producing a large share of the nation's premium vegetables, fruits, and flowers. Transparent glass panels and advanced polymer materials maximize the use of natural sunlight, while automated shading, ventilation, heating, and cooling systems continuously regulate temperature and humidity to maintain optimal growing conditions throughout all 4 seasons. Many greenhouses also incorporate hydroponics, fertigation, and autonomous robots for planting, harvesting, and transporting crops. As a result, water consumption can be reduced by as much as 70 to 90%, while productivity per square meter is many times higher than that of open field farming. Inside these facilities, premium melons, strawberries, tomatoes, and leafy vegetables are produced year-round with highly consistent quality for both domestic and export markets. One of the most remarkable examples is the Bijenheim strawberry, one of the most expensive fruits in the world. After more than 15 years of breeding, only about 500 strawberries meet the standards for sale each year, with prices reaching as high as $500 per fruit. What Japan is selling is not just a strawberry, but years of breeding research, precision greenhouse technology, and nearly perfect quality standards for size, color, aroma, and sweetness. From rice and wagyu to high-tech greenhouses, they all share one thing in common. They depend on the limited land that Japan must protect at all costs. No wall can completely defeat a tsunami, but by buying even a few precious extra minutes, Japan's Great Wall helps protect its people, its farmland, and one of the highest value agricultural systems in the world. Carrying the burden of rebuilding many of Japan's coastal communities after the devastating 2011 tsunami, mussels are far more than just seafood to the Japanese. They are a source of livelihood for thousands of families, generating more than $4 billion in economic value each year. Unlike countries such as the Netherlands, France, and the United States, where shellfish are often dredged directly from the seabed or cultivated in nearshore cages, Japanese mussels are raised on massive suspended longline systems in some of the most nutrient-rich waters on Earth. Fueled by the convergence of the warm Kuroshio Current and the cold Oyashio Current, thousands of mussels densely cover each rope within just 12 to 24 months, requiring virtually no industrial feed. When harvest season arrives, specialized vessels move along the farming lines and use hydraulic winches to haul the mussel-laden ropes from the sea onto the deck. There, the ropes pass through mechanical stripping systems, where continuously rotating rollers remove thousands of mussels in just minutes. The harvested mussels then flow onto conveyor belts and into enormous collection bags, ready to be transported to processing facilities. Once they arrive at the harbor, the mussels are transported directly to processing facilities, where they undergo a series of rigorous cleaning procedures. They pass through multiple washing tanks, high-pressure water spray systems, and rotating mechanical drums designed to remove mud, sand, seaweed, and other organisms attached to their shells. This step is particularly important because mussels are filter feeders, making them highly susceptible to retaining impurities from the surrounding seawater. After being sorted and inspected for quality, the mussels are either packaged fresh or further processed through a series of value-added operations, including steaming, meat extraction, vacuum sealing, and flash freezing. The finished products are then distributed to supermarkets, restaurants, and export markets around the world. Often referred to as the white pearl of the ocean, scallops generate approximately $3 billion in annual revenue and rank among Hokkaido's most valuable seafood products. Like mussels, their journey begins at sea. However, instead of growing in dense clusters along cultivation ropes, individual scallops are suspended separately in multi-tiered cage systems. This approach reduces competition and provides each scallop with sufficient space to develop evenly. Throughout their growth cycle, nutrient-rich cold currents continuously flow through the cages, delivering a steady supply of natural food and helping form the thick white adductor mussel that ultimately determines the premium market value of Japanese scallops. When harvest season arrives, hydraulic cranes lift cultivation lines stretching tens of meters from the sea, revealing thousands of scallops densely attached like a fully assembled production chain. The scallops are quickly removed on deck, rinsed with seawater, and transported directly to processing facilities within just a few hours. From this point onward, the process shifts into a tightly controlled operation. High-pressure water jets operating at 5 to 6 bar thoroughly clean every groove of the shell before the scallops are shucked while still alive to extract the prized white adductor mussel with maximum precision. The meat is then washed, graded, and subjected to rapid freezing at -40°C, locking in its texture and natural sweetness. By the time packaging is complete, each tray of scallops represents far more than seafood. It is the product of a seamless production chain, one in which the ocean does not merely provide the resource, but actively contributes to every stage of value creation. This is not only a battle against the desert, but also an effort to redefine a new model of agriculture for the future. So how did Saudi Arabian engineers and farmers build invisible steel rivers that brought life to an entire agricultural empire in one of the harshest deserts on Earth? That is the engineering miracle we will explore in today's video. Covering more than 2.1 million square kilometers, Saudi Arabia is one of the largest countries in the Middle East. Yet more than 95% of its territory is desert, forcing a population of more than 37 million people to cluster along the coastlines of the Red Sea and the Persian Gulf. In many regions, the average annual rainfall is less than 100 millimeters, while summer temperatures regularly exceed 45 degrees Celsius. Rivers are virtually non-existent, surface water has almost disappeared, and groundwater aquifers have been severely depleted after decades of extraction. This has left Saudi Arabia facing an unprecedented paradox. The country possesses the resource the entire world desires: oil. But the one resource it lacks is water. Despite sitting on more than 260 billion barrels of oil, it still has to spend billions of dollars just to produce every drop of fresh water. In the Middle East, oil builds empires, but water is what determines which nations can survive in the long term. That is why the country began developing one of the largest water infrastructure systems in the world, connecting giant coastal desalination plants to a water pipeline network stretching more than 12,000 kilometers, more than twice the length of the Nile River, forming a vast distribution system that reaches deep into the interior. More than just solving the challenge of supplying drinking water, this network has unlocked an even greater ambition: transforming barren deserts into industrial-scale agricultural regions capable of producing millions of tons of food every year. But to move water across thousands of kilometers through one of the harshest deserts on Earth, Saudi Arabia first had to build rivers made of steel. The journey that carries seawater across the desert begins with a massive network of steel pipelines. To withstand continuous high pumping pressure, underground impact, and the extreme heat of the desert, these pipelines must meet exceptionally demanding engineering standards. That is why they are typically manufactured from high-strength carbon steel, the same material widely used in the oil and gas industry. The process begins with enormous rectangular steel plates, pre-cut to precisely calculated dimensions. Each plate is large enough that, once rolled, it forms a pipe with a diameter of about 1.8 meters and a wall thickness of nearly 25 millimeters. The steel is then fed through a multi-roll forming machine. Industrial rollers gradually press and bend the plate until the flat sheet becomes a complete cylinder. Once the two edges meet, the pipe blank is ready for the most critical stage: longitudinal seam welding. Here, automated welding robots travel along the entire length of the pipe, creating a joint strong enough to withstand continuous water pressure for many years. After welding, the pipe is cooled with water, precision ground to remove burrs and correct dimensional deviations, and then both ends are beveled to standard specifications, allowing faster assembly, tighter connections, and greater pressure resistance in the field. At staging yards, every batch of pipes is labeled and organized according to the exact installation sequence to prevent delays during field construction. Each pipe section is typically about 12 meters long and weighs up to 40 tons. This length was not chosen at random. It represents the optimal balance between engineering requirements, system reliability, transportation efficiency, and installation along long-distance routes crossing the desert. Even a single pipeline stretching 1,000 kilometers requires more than 80,000 pipe sections, turning logistics into a massive industrial operation. Once every final coordinate has been confirmed, an invisible road begins to emerge across the heart of the desert. First, the entire surface along the pipeline route is leveled and widened into a corridor about 40 meters across, providing enough space for heavy machinery, material storage areas, cranes, and multiple construction crews to operate simultaneously. Next, heavy excavators begin digging trenches to the exact design elevation. The trenches are typically 2 to 3 meters deep, providing sufficient protection for the pipeline against surface temperatures, vehicle loads, and external environmental impacts. But the desert is not made of sand alone. Many areas consist of solid bedrock or semi-mountainous terrain, where conventional excavator buckets are almost useless. In these locations, construction crews must drill holes, place industrial explosives, and carry out controlled blasting in stages to clear a path for the pipeline. Once the trench is complete, the sharp rocks and uneven ground still cannot support the pipeline directly. A bedding layer of fine sand or fine granular material is first placed along the bottom of the trench, creating a uniform cushion that reduces localized pressure points and minimizes stress on the pipeline throughout decades of operation. But even after the trench is ready, the real challenge begins when 40-ton steel sections must be lowered into position with centimeter-level precision. Each pipe section is positioned using cranes. Before welding, a 360-degree hydraulic internal clamp is inserted inside the pipe to align both ends perfectly and maintain absolute concentricity. Even the slightest misalignment can create flow turbulence, increase stress, and shorten the service life of the entire pipeline. Once both pipe ends are secured, the automated welding system begins traveling around the circumference of the joint. But speed means nothing if the weld is not flawless. Every joint is therefore inspected using industrial ultrasonic testing to detect hidden cracks, internal voids, or alignment defects that cannot be seen with the naked eye. After inspection, the welded joint is coated with multi-component epoxy to restore the corrosion protection layer for the decades ahead. Only then do tracked side boom machines move along the construction site, lifting the entire steel assembly with wide slings before lowering it into the trench centimeter by centimeter to prevent bending or damage to the protective coating. The final stage is multi-layer backfilling. Fine sand is placed first to protect the pipe surface, after which soil and rock are added and compacted layer by layer, gradually burying the entire steel river beneath the desert to ensure long-term stability for decades. But at this point, Saudi Arabia has only finished building the road. It still has not created the water. Everything begins with the vast, seemingly endless blue ocean offshore. Instead of drawing seawater close to the coastline, where sand, oil, plankton, and pollution are more concentrated, desalination plants typically place offshore intake systems several hundred meters to a few kilometers from shore in deeper, more stable waters. Once inside the plant, the seawater passes through 2 stages of coarse and fine screening to remove all impurities, from large debris to small marine organisms and remaining organic matter before entering the treatment system. But the most dangerous contaminants are almost invisible. To remove fine sand, silt, and suspended particles that could damage pumps and filtration membranes, the seawater passes through a multi-layer sand filtration system, reducing turbidity from 5 to 20 NTU to less than 1 NTU. Next, the water is treated with chemicals to disinfect it and coagulate suspended particles before passing through 1 to 5 micron cartridge filters. the final protective barrier for the expensive reverse osmosis membranes. Then the water reaches the heart of the entire system, reverse osmosis. To separate salt from seawater, Saudi Arabia uses high-pressure pumps operating at 55 to 70 bar, forcing water against its natural osmotic direction through ultrafine reverse osmosis membranes, where only water molecules can pass, while salt, bacteria, and impurities are left behind. Before entering the distribution system, the water is remineralized and its pH is adjusted to ensure chemical stability. It is then produced continuously 24 hours a day, 7 days a week, at a scale of nearly 16 billion liters per day, making Saudi Arabia one of the world's largest desalination producers. For Saudi Arabia, desalination has never been the final destination. It is only the first step in transforming seawater into green farmland across one of the harshest deserts on Earth. Water from the massive pipeline network is quickly delivered to the desert to serve an even greater goal: achieving food security. Within just a few decades, giant green oases spread across more than 11,000 square kilometers of desert, creating one of the world's largest center-pivot irrigation systems. Throughout the growing season, automated irrigation systems continuously adjust the amount of water according to the crop's needs before combine harvesters complete the entire harvesting process. By the late 1980s, Saudi Arabia was producing more than 4 million tons of wheat every year, not only becoming fully self-sufficient in domestic demand, but also exporting wheat to international markets. However, this success also led to the excessive depletion of groundwater aquifers, forcing the country to gradually end its wheat self-sufficiency program and shift toward cultivating higher-value crops. That was also the moment when the precious water flowing through the desert was redirected to an agricultural industry that has been part of Saudi Arabia for thousands of years: date palm cultivation. In regions such as Al-Qasim, Al-Asa, and Medina, millions of date palm trees are planted in perfectly aligned rows, forming one of the largest date-producing regions in the world. Drip irrigation systems deliver water precisely to the base of each tree, while sensors continuously monitor soil moisture to minimize water loss. When the harvest season arrives, specialized lifting vehicles raise workers to the tops of trees, standing more than 10 meters tall, where they cut individual date clusters weighing tens of kilograms. At many large plantations, hydraulic lifting platforms and mechanized equipment have replaced most traditional climbing work. Today, Saudi Arabia is one of the world's largest date producers, with an annual output of more than 1.5 million tons and exports reaching more than 100 countries. This industry not only generates hundreds of millions of US dollars in export revenue, but has also become one of the pillars of Saudi Arabia's agricultural economy. It stands as the clearest proof of how water infrastructure and technology have transformed the desert into a large-scale agricultural powerhouse. Water has not only transformed the desert into farmland, but has also made it possible for Saudi Arabia to build one of the most advanced dairy industries in the world. Almarai alone, the largest dairy company in Saudi Arabia, operates nearly 200,000 dairy cows across 8 industrial-scale farms. Even more remarkable, each cow produces an average of more than 12,400 liters of milk per year, exceeding the average productivity of many countries with highly developed dairy industries, including the United States and New Zealand. To protect the herd from the extreme desert heat, the barns are equipped with powerful ventilation fans, evaporative cooling pads, and misting systems, maintaining suitable temperatures for the cattle throughout the year. More than 12,000 kilometers of pipelines, dozens of desalination plants, vast wheat fields, date plantations, and modern dairy farms have demonstrated that even a country where more than 95% of the land is desert can build a large-scale agricultural industry if it can solve the challenge of water. Do you think projects like this represent the future of agriculture in the world's arid regions?